Hello everyone. We've already started a lot about proof of work, its advantages, how does it really work, the steps involved. In this, we're going to study about its properties. Proof of work is basically a race where everyone is just competing to solve the complex puzzles because those complex puzzles aren't really some sudokus, right? Your average sudokus or something. They are cryptographic hash puzzles and it takes a lot of computation power to solve them, right? So, difficulty varies with time. With time, the difficulty of the puzzle also increases. In fact, if you talk about 2015, the difficulty level was over 10 to the power 20 hashes per block, right? As it's mentioned in the deck. To put that in the perspective, just think the size of the target space was smaller than 1 in a quintillion of the hashed output space. That is less than, it's less than equal to 1 by 10 to the power 20. Now you think you can compete in this race with a regular laptop? No. Even before you start competing, you're totally out of the race. So only some nodes in this case called miners actually bother to compete because they've got that computational power that is needed, right? So they are the ones, repeatedly solving these hash puzzles in a way that we call Bitcoin mining. Technically, if you ask me, anyone can mine, but in reality, no. Mining power is concentrated in a small specialized ecosystem, the ecosystem that has the computational power that is needed. Because if you do not have that, you're just cheering from the sidelines. If you don't have the serious hardware, if you don't have the serious computational power, you're just cheering from your sidelines. So the next time you hear about mining Bitcoin, remember it's not just luck, it's competition, and some seriously heavy maths that is involved, right? With this, let's come to the next property that goes by parameterized cost. Now let's just talk about how Bitcoin keeps things fair with the parameterizable cost. Miners aren't just blindly guessing hashes forever. They take up a nonce, they just move it, increment it, right? And the network automatically recalculates the target, your hash space target, basically the difficulty, every 2 weeks. Why so? Because the average time between the two blocks has to be kept at 10 minutes. And technically speaking, this recalculation happens every 2016 blocks, roughly 2 weeks. Think of it as the network constantly adjusting its hurdles to keep the race on track. And here's the key insight. Your chances of winning the next block aren't random. They're proportional to the fraction of the global hash power that you control. So let's say if your Alice controls 5% of the network's hash power, she has a 5% shot at mining the next block that she would be chosen to to propose the next block. The chances are directly proportional to how much hash power you have, to the fraction of the hash power that you have in the system. So you can see a formula on the deck, right? Probability of Alice winning the next block is equal to the fraction of global hash power she controls. To give a better perspective on this, I would just like you to imagine a huge lottery where miners are buying tickets by solving really, really, really hard puzzles. So the faster your computer, the more tickets you have in the lottery. And let's say Alice is one of the miners in between. Her chances of winning the next block, or I would say her chances of being nominated, of being selected among the pool to, to give up, to propose the next block, are directly proportional to how much computing power she contributes compared to everybody else in the network. For example, let's say Alice has 10% of the total mining power. She has roughly a 10% chance of winning the next block, of, being nominated to propose the next block. Now, let's say she upgrades her machine, doubles her power to 20% of the network. Now her chances improve and it becomes 20% because it's directly proportional. The more powerful your mining setup relative to the whole network, the higher your chances of mining up a block. I hope you understand that. Now the question, why is the recalculation needed? Why we don't just let miners go full speed? Why do we have the 10 minutes in between? If blocks are proposed too close to each other, it becomes inefficient. Imagine trying to stuff multiple transactions into a block while the new blocks are still coming up. That's a total chaos, right? And that is where we have this 10-minute rule come in. On an average, a block is mined every 10 minutes, giving enough time to process, to group your transactions before the next block comes in. So, you'll be asking me, is 10 minutes sacred? Is 10 minutes like it has to be 10 minutes? No. The system could actually work with 5 minutes, the system could work with 10 minutes, or even some another time frame. The key is that we're giving the network a sufficient time we can to adjust the difficulty dynamically to maintain the chosen interval. The blocks have to be pushed up after the 10 minutes, right? So in short, readjustment keeps the blockchain orderly, efficient, predictable, making sure transactions just don't get lost up. Now, let's talk about the security assumption, right? It's actually the backbone of Bitcoin, or if I rephrase it, the backbone of blockchain. So the key assumption behind Bitcoin security is simple. Attacks become practically infeasible if the majority of the miner nodes are honest nodes. They're weighted by the hash power. They follow a protocol, right? Or simple words, they're honest. Because that much hash power is needed, that much computation power is needed, and to that basis, that much hash power is needed, and it becomes directly proportional to you being the next person to be chosen to propose the next node. So more the hash power you have, more are your chances to to be elected up to just to be proposing the next node, to be proposing the next block. So this ensures that at any given moment there's more than 50% chance that the next block is mined by an honest node, keeping the blockchain secure, keeping the blockchain tamper proof. So as long as the honest miners hold the majority, Bitcoin stays resilient against attacks. And in a way, you think that's a clever way of turning your collective honesty into robust security, because you're maintaining the majority in the system. You're maintaining a majority in the network. So next, you see a probability density versus a time to next block graph. We take it to be the 10 minutes that we're keeping in between two blocks. And yeah, the mean time to find block, 10 minutes over the fraction of hash power. We've already seen this. Next point comes trivial. It's trivial to verify, because okay, there's an equation. I ask everybody listening to solve that equation. It would take you considerable time. But if I tell you, see, this is the equation, x is 3. Can you verify if x is 3 satisfies the equation? It is relatively easier. Much, much, much easier, right? Just have to take the value, plug in. Simple. You don't have to think about, and what if I'm telling you, you have to solve that equation, but you have to go increment by 1. So you take x0, the equation returns false. You take x1, the equation still returns false. And maybe going to x is equal to 101, 131, you get an answer. But what about till that step? You have to do it incremented, right? One on one, you checked it for everybody. Now I straight away tell you x is 131. You just got one value. You have to plug in that value into your equation, find the answer. If it holds true, well and good. If it does not, it's not the answer. So simple. So that is to say, it's very trivial to verify. And the advantage that it gives you, no central verifier needed. Any node or miner can verify the block that was correctly mined. Now let's come to the mining part. Mining Bitcoin, it sounds exciting, right? But it comes with its fair share of complications. If your mining reward does not exceed your, all the costs that you've incurred in putting up that system, that is actually non-profitable for you. So let's just talk about the complications first. There are fixed costs like buying mining hardware, variable costs like your electricity, and these both add up, right? And there's another twist. The costs are in dollars, but your rewards comes in Bitcoins. So your profit actually also depends on the exchange rate. Bitcoin could go up or down, changing the math entirely. Now it depends on what the exchange rate is going on, and that is what defines your profit. But even then, given all this, given everything this, solving over 10 to the power 20 hashes to earn 6.25 BTC can still be profitable at the current exchange rate. And if you've got the resources, if you've got the patience to compete in the mining race. Now let's clear up some common misconceptions about attacking Bitcoin. This is the last slide for today's video lecture. So let's just clear about some common misconceptions that I have heard, I have seen in my, all this life. Can someone steal coins from an existing address? No. The cryptography keeps your funds safe. Coming to next. Can someone suppress transactions? Well, kind of. They could delay transactions in a block that is already being mined, but not on the peer-to-peer network. The rest of the network will still broadcast and validate transactions normally. So they can do that for a particular blockchain, but they cannot do it for a P2P network. Can the block reward be changed? It's a clear no. The rules are hard coded already into the protocol. You cannot change the protocol anytime you wish to, right? Destroy confidence in Bitcoin. It is possible. It is actually very much possible to erode confidence in Bitcoin. If people start doubting the network's integrity, in cryptography, in crypto, in blockchain, in Bitcoin, confidence is everything. Confidence is money. That is what is making people on, other ends of the world collaborate, communicate, and actually transfer money, have transactions, right? So yes, they can destroy confidence in the Bitcoin. With this, I would take your leave. We'll be starting with proof of stake in the next video lecture. Thank you so much. Bye bye.